Hey everyone, my name is Mano Mata, and today I'm going to be talking to you about rotating detonation engines. So let's start with some background. Standard combustions in modern-day gas turbine engines consist of deflagration. Deflagration, the term which is underlined, is a combustion process where the combustion front propagates at subsonic speeds. Because of the modern design of combustors, the deflagration combustor is open to pressure loss from heat transfer and aerodynamic design. To combat this, engineers started looking for other possible methods of combustion. One of these methods is a pulse detonation engine, where a detonation wave is created and that moves down the channel at supersonic speeds. This wave actually compresses the flow because of its supersonic nature. Thus, this combustion process leads to no pressure losses. Some downsides to this, though, are that it's very loud, it requires more energy to start, and it's limited by mechanical parts. But theoretically, it is more efficient than deflagration. On this slide, we have some images. On the left, you see deflagration. It has a continuous slow burn, whereas the pulse jet on the right opens its valves to release air and fuel into the combustion chamber, and it ignites the wave, so it moves a lot faster. The design on the right, the pulse jet, is limited by mechanical parts, as the goal is really to have the pulses happen so frequently that it's almost like it's one continuous combustion. The design is limited by mechanical parts as the valves have to open up over and over again, and that obviously can't happen that quick. So those top out at around 250 pulses per second, but a theoretical one would have around 1,000 pulses per second. So the next step in that is rotating detonation engine. What is that? So let's get into that. Here's some of the basics of what a rotating detonation engine is. It is a similar concept to a pulse detonation engine with the goal of using detonation waves to add a pressure rise through the combustion process. The one difference is that instead of having a wave that has to be constantly purged in the chamber, there is a continuous rotating detonation wave that moves around the combustion chamber. This is better than a pulse detonation engine because the combustion is continuous. It makes the design somewhat simpler, and the combustion chamber does not have to be continually purged. The flow of oxidizer or air and fuel can be constantly pumped into the combustion chamber without interruption. So here we have a picture of the visualization of the rotating detonation engine's detonation wave. So you can see that front that's moving around. That's where the red starts. That's the detonation wave that's moving at supersonic speeds. And you can see the sharp temperature rise just past it. This is only an example of one wave. This design only has one wave, but there are other designs that can have multiple waves. This all depends on the fuel as well as the size of the combustion channel. So let's talk about some current difficulties and drawbacks. The first one is that technology is still being matured. So some research has also shown that the flow characteristics at the exit of the combustion chamber show a lot more unsteadiness, and there are higher temperatures associated with that when it's compared to a deflagration combustor. This will probably require a redesign of the turbine blades as well as the guide vanes that are closest to the combustor to better control the flow and extract most of the energy. There's also another drawback here that because of this, this RDE, the rotating detonation combustor, cannot be directly replaced with the deflagration combustor cannot be directly replaced with a rotating detonating combustor. So some of the inlet and outlet designs might need to be changed as well. Some successes in current work include JAXA, which is the Japanese Aerospace and Exploration Agency. They recently conducted a test of an RDE in space to see if it was more efficient for interplanetary missions. It was a smaller scale engine, but it showed promising results. Purdue, NASA, and other government agencies have also invested a lot of money into rotating detonation engine technology research. We'll see a demonstration of that later. One of the papers I read talked about replacing a deflagration combustor with a rotating detonation combustor in an Allison T63 gas turbine engine. This was put in an open loop configuration, which means that pressurized air and fuel were pumped directly into the combustor instead of the pressurized air coming through a compressor. And the efficiency was read by seeing how much work was extracted from the turbine. The results showed similar efficiency between the deflagration combustor and the rotating detonation combustor, and this was also tested on various fuels. There's also been work done looking into ground-based gas turbines with natural gas as the fuel, although results there were not as promising for that study. Here's a demonstration of Purdue's engine. So you can see it's a smaller scale. It has very low mass flow, and the equivalence ratio is also close to 1. So you can see how quickly they run that test. And now you'll see some slow-mo footage of how the detonation waves propagate around the channel. And you can see how fast they're moving. And there's 2 waves in this one. You'll also see a side view of that, which is pretty cool. And they were able to do that. And this is from a couple of years ago. So that means that this technology is already progressing quite well. So some final takeaways is that this technology still needs investment to be further developed and matured. It shows the possibility of being more efficient than regular deflagration combustors, and it doesn't have the most success yet in the gas turbine area, but you can still see it being applied to space propulsion. Thanks for watching.